Hey everybody, I'm Jesse Udall. Welcome to my presentation on technology transition for CEE 300 Engineering Business Practice at Arizona State University. This presentation will be answering the question of which light bulb is the best choice for a person living in the Phoenix, Arizona area over a 20-year period. There is so much terminology with light bulbs that it is difficult to understand everything about them. In this video, I will try to make sense of as much of this as possible in order to aid in making the best decision on which light bulb to choose. With the wide variety of light bulbs available today, instead of looking for a specific wattage of a bulb, it is better to check the lumen output of the bulb. More lumens means brighter, and fewer lumens means dimmer. Why is this so important? As you can see from this table, each bulb type puts out the same amount of lumens, or the same amount of light, but the CFL and the LED bulbs require much less energy to do so. Another important thing to look at is bulb life. Incandescent bulbs last about 1,000 hours, or approximately 1 year. This is assuming that the bulb is turned on for about 3 hours each day. CFL bulbs will last around 10,000 hours, or about 10 years. LED bulbs will last for as much as 50,000 hours, or approximately 50 years. Also, we will be using an average of 10 cents per kilowatt hour for our electricity cost in this analysis. In this slide, I've condensed a lot of the information that we'll be needing to do our analysis. So we have our lifespan of each of the bulbs, how many watts each of the bulbs uses, how much each bulb costs, how much electricity or kilowatt hours is used over 1,000 hour period, how much each bulb costs to run over a 1,000 hour period at 10 cents per kilowatt hour, and how many of each bulb type will be needed over the lifetime of our analysis. In this analysis, I will also be considering the heat output by each bulb and the air conditioning interaction that this has within your home, as this also contributes to how much it costs to operate the bulb over its lifetime. This analysis will be done on what is an average house size here in the Phoenix area of 2,500 square feet, and this house will be assumed to have 8-foot ceilings. As you can see, each bulb has a specific amount of inefficiency along with it. That means that this percentage of energy used by each bulb is converted to heat energy. For each bulb, you can see how many watts of heat energy are put out whenever each bulb is turned on. So, let's see how the heat output from each of these bulbs affects the temperature inside of the house. This first equation is just a form of the first law of thermodynamics. Q dot represents the heat output, which we've solved for in the previous slide. M represents the mass of the air inside of the house. Cp is the specific heat of the air at room temperature, or approximately 80 degrees, and we will be solving for delta T. Now you can note that I have converted my units from the British to SI units, as they are easier to work with, and we will convert them back once we have finished our calculations. Also, you should know that your delta T value will come out in degrees Celsius per second. You will need to multiply this by 3,600 in order to get your hourly temperature increase. Also, watts are known by the units of joules per second. So in order to get your hourly joules emitted, you'll also need to multiply your heat emitted value by 3,600 as well. Let's learn a little bit about air conditioning units. Most AC units come rated in tons of refrigeration. 1 ton of refrigeration is approximately equal to the cooling power of 2,000 pounds or 1 ton of ice melting in a 24-hour period. This value is defined as 12,000 BTU per hour, and 1 BTU is approximately 1,055 joules. So you can do the math from there to figure out how many joules are in 12,000 BTU. Most residential AC units range from 1 to 5 tons of refrigeration capability. And if we take the mean, 3 tons, from that range, this unit would be capable of cooling 3,798,000 joules of heat energy every hour. Also, a 3-ton unit uses 3.5 kilowatts of electricity to operate. This converts to 35 cents each hour that it is running. Using this simple formula, we can figure out how much it costs to cool the heat output by the light bulb each day. Simply take the heat emitted by the light bulb, divide that by the cooling capability of the AC unit, and multiply that by the hourly cost to operate the AC unit, and you'll have your daily cost of cooling per light bulb. In order to figure out your yearly cooling cost, this will be defined by the cooling season, which for Phoenix is approximately 171 days. I just assumed that any day that the temperature is above 90 degrees Fahrenheit, your AC unit will be running. Here is our cash flow diagram for our incandescent light bulb. Notice the small initial cost to purchase the bulb, but the annual cost thereafter is quite a bit higher. Here is our cash flow diagram for our CFL bulb. We have our initial cost of $3.95, and then our recurring annual cost to operate the bulb. Notice, at the 10,000 hour mark, or approximately 10 years, we have a large spike in our cash flow. This is where we must replace our bulb because it is no longer functional. Here we have our LED cash flow diagram. Notice our extremely large initial cost to purchase the LED bulb, but our cost to operate and cool the heat emitted from the bulb for every year thereafter is extremely low in comparison to the others. Also, we don't have to replace the bulb in this period of time. Now we are at our most important part of the analysis. Here we must take each cash flow from the points on our cash flow diagram and calculate how much that payment would be worth in today's money. For a single payment, we have several variables, including FV, which represents some future value at some point in time. I represents the discount rate. This rate can vary depending on the person and their own situation. It is not the most intuitive concept, but it is a way of explaining that money in the future is worth less than it is at present. Therefore, this future amount needs to be discounted to account for this change in time when converting that sum of money to a present value. N represents the period in the future in which the cash flow is occurring. We have pretty much the same variables for a recurring payment. The only difference is we have this variable A. A is the recurring amount of the payment that you're making in each period. For example, for the incandescent bulb, we have a recurring payment of $16.85. For the CFL, it's $3.38, and for the LED, it's $2.19. Now, we've done all of this work to get to this point. We just take the values from our cash flow diagram and plug them into our formulas, depending on whether it be a recurring payment or a single payment sometime in the future. I have assumed a discount rate of 5% as an arbitrary value for this problem. Plugging these numbers in, we get the following values: $211.24 for a net present value for the incandescent bulb, $48.50 for the CFL bulb, and $63.24 for our LED bulb. So what's the best bulb? The CFL. Thanks for watching.